Good evening, and welcome to this SEIO Women in Statistics and Data Science for Common Good session. We are going to begin with the first speaker, which is Jessica Rodriguez-Pereira, who is current Ramon y Cajal researcher at the Polytechnic University of Catalonia. She also studies civil engineering, master degree in logistics, and PhD in statistics and operation research. She has held research stays in several university and research center in Germany, Canada, among others, and a university in Spain like Pompeu Fabra. His research focused on the study of mathematical optimization model for solving problems related to logistics, transport, and network design. She has received several awards. Research is mainly focused on problems related to logistics, transport, and network design. As a result of her research work, she's co-author of research articles published in prestigious scientific journal and has participated in both national and international conferences and projects and collaboration with organizations for social good. Jessica, you are going to present mathematical models and humanitarian operations. Maybe you are ready to share the screen for presentation. Yes, thank you very much for being here. You can start when you want.
Thank you very much, María Dolores. Good afternoon, everyone. First of all, I would like to thank the organizers for inviting me to be here. Sorry. Are you seeing my slides? I guess so. So I'm here today to share part of my research, and I will be showing how mathematical models can support humanitarian operations, focusing on a case study that involves the restoration of drinking water supply system in the rural areas of Nepal. For those who are unfamiliar with disaster management, its primary goal is to reduce the negative impacts of a disaster. This is achieved through mitigation and preparedness before a disaster occurs, but also with response and recovery afterward. In this field, statistics, data science, and operation research offer valuable tools and insights to help achieve this goal. Let me briefly introduce the project focused on restoring drinking water supply system in rural Nepal. This initiative was carried out in collaboration with the Austrian Red Cross and the ZGs from the University of Salzburg, and it concentrates on the recovery phase. As you may recall, Nepal was strongly hit by two major earthquakes in 2015, one in Gorkha district and another in Dolaka district. These events caused thousands of deaths and large-scale damage to buildings and infrastructures, as we can see with this temple. Most of the affected area were rural areas with difficult access. In these areas, over 1 million people lost access to safe drinking water due to the destruction of the supply systems. The Austrian Red Cross, in collaboration with other local NGOs, aimed to rehabilitate damaged water supply systems and was interested on developing an optimization tool to support this rehabilitation. Their main objective was to decide where to locate a minimum number of community water taps such that people could access them within the national wash standards. The secondary objective, of course, was to build also the gravity feed system to ensure that those water taps are connected to the water source. So at the end, this involved two key decisions. The first one, and the primary one, were to locate the water taps, and the second one, how to connect them to the water sources. This slide shows an example of solution. So you can see how households are assigned to a community water taps, and then the network connects these water taps to available water sources. Since we have multiple water sources and a same water source can be accessed from different points, what we are looking for is what is called a Steiner's forest network, which allows also to have bifurcations at any point of the network, so we optimize the network layout. One of the main difficulties is to ensure all the characteristics. In terms of the water tap placement, must comply with the national wash standards. This defines which is the maximum walking distance people must walk to access the water tubes. So in the preferable cases, the horizontal distance should not exceed 150 meters, and the vertical distance should not exceed 50 meters. However, we can allow in exceptional cases these limits to be extended to 250 meters in horizontal and 80 meters on vertical distance. Moreover, one of the difficulties of this project was that Nepal is a mountainous terrain, so water distribution relies on gravity-feed systems, that meaning that pumps are not allowed because they are costly and hard to maintain in these rural regions. So we need to ensure two technical conditions to satisfy this kind of gravity-feed system. The first one is that no point in the pipeline in all the network can be higher than the water source. Although pipes can go up and down, we need to ensure that no point is higher than the water source. And also, we need to ensure that the system satisfies the Hassen-Williams equation. This is a equation to ensure pressure of the water. And it's based on elevation of 2 points, any point and the water source, the distance between these 2 points, and also the pipe characteristics, like rugosity, material, and so on. So to support this decision-making that Red Cross wanted, we developed an efficient metaheuristic using geographic and water system data. The volume of data that we had, especially the geographic, was substantial, and it requires extensive processing. We work with real data from two communities, Suspa Hasemawi and Lapilan. Due to the large extension, each of the region was discretized into a grid of 25 at 25 meters, resulting still in a large graph with around 29,000 of vertices and 70,000 of arcs. But based on the data extracted from satellite imagery with the collaboration of the CGIS department at Salford University, and based on this discretization, each cell's information was concentrated at its centroid, allowing us to model this problem as defined on a simple graph, long graph, but at the end a graph. So based on this, as mentioned, we develop a metaheuristic that combines exact and heuristic methods to solve the problem in a hierarchical way. Why in a hierarchical way? Because the problem was too difficult to solve it together, and we were able to do it hierarchical because we were exploiting the nature of the problem, where providing water in the standards is more important than the cost of the network. So we need to ensure the service. This is the primary objective of the NGO, but of course we need to provide the network. So what we did was first solve exactly which was the water tap location allocation problems. So we were able to identify the location of the water taps and the household assignments by minimizing the number of water taps to install, but also the average walking distance. And then once we have defined the water taps, we solve the design of the water network. For that, we use a cluster first 3-second heuristic to design the stainless forest network. Here in this image, show for two different weight settings the solution of the first part of the location of the water taps. You can see with the pink circles where the water tap should be located. On the left image, you see the location when we are only minimizing the number of water taps. That was the original goal of the NGO. But based on the result, they realized that even with these results satisfy the standards, it was not a likelihood solution. On the right, you have another solution in which we also give way to the average distance. In particular, we are given a weight of 0.25 to the number of water taps, 0.35 to the preferred distances, and 0.40 to exceptional distances. Sorry. If we compare the number of water taps on both solutions, of course, we go from 88 when we minimized only the number of water taps, and it increased to 111 by also taking into account the distances.
Sorry, Jessica, only 3 minutes.
Okay. This table summarizes the results for the different weights, and at the end we recommended the selected setting, 0.25 to the water taps, 0.30 and 0.45 for the walking distances, because this offers short walking distances without significantly increasing the number of water taps or the network length. Here is the network solution for Lapilang using the recommended weight. As you can see that the Steiner vertices, which are the red diamonds, are readily used. So in general, pipes go from one water tap to another, although bifurcations were allowed. In conclusion, we develop a math heuristic capable of computing quickly a solution that satisfies several technical features, such as the accessibility within the WASH standards, but also the gravity conditions, taking advantage on the hierarchical structure of the problem to solve it sequential as to subproblems. We tested the methodology on large-scale realistic data from 2 villages in Nepal, and I want to finally note that to ensure that the proposed solution is adequate to the mountainous character of Nepal, we work with distance that also incorporate elevations, adapting the Dijkstraat-Shortest algorithm to the three-dimensional distances. Thank you very much for your attention.
Thank you very much, Jessica. It's very interesting talk and very useful. Beautiful. We have on time, but maybe for questions, I don't know, in the chat, maybe later, because we are very short time. And then maybe it is better to continue with the next speaker, which is Begoña. Begoña Vitoriano is Associate Professor at the Department of Statistics and Operation Research and the Interdisciplinary Mathematics Institute for Complutense University of Madrid, PhD in Mathematics and Operation Research, and she has been University lecturer in 1999. Begoña is a very active person in leading several projects along her career, and also currently she leads a lot of international cooperation and research projects, and she is author of more than 60 publications, some of them being references in the area, and she has been coordinator of several PhD master programs in the Complutense University and several master in statistics in Salvador, Peru, and Mozambique since 1996. She has been the SEIO president during the period 2022 to 2025 being currently the SEIO past president 2025 and 2026. She's going to present today data science for decision-making in disaster management, scenario generation for stochastic optimization. Thank you, Begoña, for sharing your research and your work and to be here.
Thank you, Lola.
Thank you.
Okay, can you see the presentation and hear me?
Yes, we can. Yes, thank you.
Thank you very much. I'm going to present a work that we are developing with a colleague of my university, Complutense University, and one colleague of University of Oviedo, Adam Rodriguez. This is devoted to uncertainty in data science and stochastic optimization. So the first part is the context is the disaster management cycle, as Jessica has presented. It's in disaster management or humanitarian operations, we have a cycle with prevention, mitigation, preparedness, response, recovery, and finally evaluation to begin again, to evaluate different actions for mitigation and prevention and so on, with two elements, uncertainty and time pressure. Uncertainty in the part of prevention mitigation, we have a high uncertainty because we are preparing for future disasters. It's not happening anything. So, but we can develop models and tools that they need some time because we are not doing it under time pressure. Time pressure arrives when the event strikes an area, a landscape, a community, and so on. For the humanitarian operations and support the people, affected people, there is a key set of actions that is humanitarian logistics. Humanitarian logistics is the process of planning, implementing the goods and storage of goods and materials and related information from the point of origin to the point of consumption. In the case of humanitarian logistics, the purpose is alleviating the suffering of vulnerable people. We work especially in assessment, planning, procurement, warehousing, and transport. And decisions should be made on different time horizon because we have strategic decisions, tactical, operational, and real-time monitoring and evaluation. So I'm going to present a decision support model for preparedness. It's based on deciding strategic and tactical decisions. Many countries suffer recurrent natural disasters, and many of them are seasonal disasters, especially those related with climate and climate change. There are many of them are sudden onset disasters. In this case, authorities must provide relief aid to affected people under a very high time pressure. So prepositioning of the relief aid is key to achieve the people in needs in the first hours. Big amounts of relief aid to be moved in short time, and first responders are population, civil protection, local civil protection, governments, local NGOs. So local capacities are critical to respond, especially in the first 70 to 72 hours, because the international support will take some time to arrive. So our model tried to give a response for strategic decisions on when and where to locate the main warehouses and what is the capacities have to. Tactical decisions is how much humanitarian aid to be prepositioned, especially in each season of the year, because the recurrent disasters usually related to climate and to the weather, so are different over the year. So how much humanitarian aid to be prepositioned, where to locate this prepositioned aid, and what budget should be saved for attending the facilities, maintenance, and so on, and maintaining stocks, and for response. But how to evaluate these decisions? These decisions must be evaluated on the disasters. So we need to include some operational disasters, the operational decisions on scenarios of disaster scenarios. In these disaster scenarios, we represent, simplified, how transport the goods that are stored, and also new budgets and emergency, how much humanitarian aid to be acquired in emergency, and how much humanitarian aid should be acquired late afterwards to restore the stock levels decided on the tactical decisions. So we have developed a preparedness model for strategic and tactical decisions evaluated in different operational scenarios. Our model has a time horizon of several years, because it's a planning for expanding and maintaining capacities. Some periods into the years related to the season, into climate season or weather season into a year, and the landscape is very important. So we are representing and going to illustrate this model with application in Mozambique. So we have the districts are nodes of the graph. We have here is the map of Mozambique. Here is 3,000 kilometers, and here is the graph that will represent this landscape and the road network. So each scenario for its season must represent the people and affected area where is located the people. It means the demand of relief aid in each node and the roads conditions for distributing the relief aid. We have several criteria to evaluate the decisions, and some of them, two of them, we work mainly with these two criteria, is effectiveness and efficiency. Effectiveness is related to reach the objectives of the operation, and we measure with the unmet demand in these 3 first days after the disaster, and it will be stochastic because it's different in each scenario. So we work here with expected values as is a repeated operation over time. So, and efficiency is the budget deviation. That also is a stochastic, because we have a deterministic strategic cost is deterministic for the facilities, but tactical and operational costs are stochastic, and use also expected value and multi-objective optimization to obtain the Pareto frontier. So how to obtain the scenarios? Okay, we have developed a methodology to obtain scenario generations. The scenario features is a weight of probability of occurrence, the demand of each commodity in each node of the network, and the capacity of the network, the links in the network, and transport cost of a commodity through the link. Data sources for a scenario generation, as they are recurrent disaster, we use historical data, whose consequences are very independent on the type of disaster and the location. So for each location and type of disaster, we have small data. It's the opposite to big data. And the information is scarce, reliable, especially for developing countries with bad or free information register, and several data sources. In Mozambique, we have the slow onset disasters, but our model is especially for sudden onset, floods and cyclones, especially, being also seasonal. We have seasonal drought, but we work with floods and cyclones or storms. Data sources. Well, there are some historical data on databases, especially MDAT, is very known database for people working on disaster management, but the geographical distribution is very light. It's not appears exactly the places affected by the disaster. There is another database that is being promoted by OCHA, that is the Sinventar, that is collaborative, is very more precise, but it's very unreliable because it's based on people, including their knowledge. We have also used Google Maps, Mozambican entities with meteorology, transportation, information of the logistic cluster, and NGOs, Red Cross, and so on. So the procedure, we have 5 phases. The phase 1 is to obtain global demand classes for each type of disaster. It means scenarios for the total amount of people in need of people translated in goods in it. So we propose a model, optimization model, for fitting a discrete distribution, fitting the moments of a continuous distribution estimated with data. Okay, and so on with other conditions like inclusion. The worst case should be at least worse than the worst historical case, and so on. It is applied for the Mozambique. We obtain for storms and floods with data that we have more or less some values of disaster, limiting the number of disasters. The second phase is a fuzzy classification, is to allocate the historical data cases in the different scenarios of global demand that we have obtained. For this thing, we have defined a distance based on the distribution function, assuming a log normal distribution on the amount of global need. Okay, so for instance, for flood scenarios, we have this data. In phase one, you obtain these 6 scenarios of global demand, and each of these cases there is a belonging function to each of the scenarios. So the color make the intensity of the color is higher value of the belonging function. Okay, this is for floods, this is for storms. And the next phase is obtain geographical scenarios from these scenarios. Is for each of the scenarios and the cases allocated in the scenarios in the class to obtain geographical scenarios. We have to define a new distance metric, a new metric to make the distance between cases and centroids, and complete later scenarios with information on road damage, and so on. It means, for instance, this is the flood scenarios, and this is transformed in 6 scenarios in these 18 geographical scenarios. And for storms, we obtain these 16 scenarios, geographical scenarios on the map of Mozambique. Okay, the next phase is merging the scenarios of different disasters in the same season to obtain
3 minutes. 3 minutes.
Okay, aggregating consequence and to make later a scenarios reduction with a threshold and defining the number of scenarios which will define the model dimensions. This is the application to Mozambique. This is the map of Mozambique with the districts and the transport links, but only the red ones are paved ways, and also with the rivers showing the vulnerability of the links because they are big rivers. Mozambique is Zambezi, Limpopo, big rivers. Okay, we have been working on one province of Mozambique, Nampula. It's here. This is the map. The model is applied with 5 years for planning and 4 seasons per year. 21 districts and 7-8 links between districts, 35 scenarios, not all of them in its season, leading to a big model to be solved. And here you can see the Pareto frontier, in which we have running 8 cases. This is, for instance, here we have the expected unmet demand, and here the expected budget deviation. And we have here one case that corresponding to a final distribution of relief prepositioned or capacities, for prepositioned aid. This solution, this is with the less unmet demand, but the higher cost correspond to a higher prepositioning capacity prepositioning. We have the 8 cases until this one on here, this one that is the less amount prepositioned, less capacities, corresponding to a higher unmet demand and the lower the deviation cost. So the decision maker should choose which solution, which is the solution, the compromise between both criteria to define which is the amount. Actually, we are working with the authorities for other province. In Nampula, we couldn't work with the authorities until now, but now we are working on another province with the authorities, that is in Yamane provinces. So the conclusion is that we can produce models for planning on repositioning and so on, but we need data and we need to represent the uncertainty in our models, and especially scenario generation to develop later the stochastic optimization models that to give response to this need. Thank you very much.
Thank you very much, Begoña. It is very, very complex, but very nice also. Beautiful talk. But we are now in 2030, so we have to go to the next speaker. Maybe during the last minutes in the chat, we can formulate some questions. So we are going to present to our last speaker, who is Lola Martínez Miranda, is full professor of statistics at the University of Granada. She has been a member of the Department of Statistics and Operation Research since 1994. She started in non-parametric regression at the University of Granada, and also she was awarded with a fellowship for career development in the Marie Curie Intra-European Fellowship Framework for 2 years. As senior research fellow in Bayes Business School City University of London, she developed an interdisciplinary research project in mathematics with high impact in the insurance industry. She has published more than 40 papers in Journal Citation Report Indexes Journal, and she is also associate editor in several prestigious journals, statistical journals. She is currently president of SEIO since June 2025. Thank you, Lola, for being here and for your presentation when you want.
Okay, thank you very much. Can you hear me? Can you see the presentation?
Yeah, we can see. It's perfect.
Okay, thank you so much for this very generous presentation, and good evening from Granada to everyone, and congratulations to all women. Thank you to the lovely people making possible this big celebration. I'm really happy to be able to contribute with a piece of research of my own. So it was about 5 years ago when the COVID-19 changed the world. And maybe one of the most surprising effects of the COVID-19 pandemic was the sudden public interest in statistics, and especially in data. Suddenly, people were checking daily numbers of positive tested individuals, of hospitalization, deaths, just trying to understand difficult epidemiological concepts such as the reproduction number, the R number, following almost impossible forecasts, just trying to see when this nightmare was going to end. And I think statisticians played a crucial role in helping society to understand what was happening and advancing what was going to happen. I think it was one of these moments where everyone could see that really statistics was truly serving the common good. And I think now we need to be careful that we don't forget what we have learned. And one thing we learned is that we need to be better prepared next time, because COVID-19 pandemic was not the first pandemic, and for sure it's not going to be the last one. So I'm going to present here a piece of work I've been working with some co-authors. What we try to do is to provide some kind of benchmark approach that one can apply to monitoring and forecasting a developing pandemic from the very early stages, because we thought that this was something missing at those times. And with this in mind, to provide this kind of tool, there are several things one need to take into account. The first thing that one should think is that in the COVID-19 pandemic, one thing would happen was that the lack of data. So the data were very scarce and they didn't have much quality. So actually the kind of information one could expect at the beginning of a pandemic is the information you have in the newspapers, in the public website, which basically were counts. So these data are not only the more reliable data you could have, but also they are standardized in such a way that you can do cross-country comparisons. Another thing you need to take into account when doing this kind of benchmark approach is that this is an interdisciplinary work. So it means that it requires communication among people. So it means that the benchmark approach that we want to provide should be something easy to communicate, something transparent. Everyone should understand what is the input, what is happening inside. And also it should be able to incorporate expert knowledge, because there are a lot of expertise that we need to use if we want to forecast. So when choosing or feeding our benchmark with the available data, we are aware of the statistical challenges behind it. This is how a typical available data at the early beginning of a pandemic you can expect. Basically, they are counts. You are counting people every day. So what happened with this kind of data when you look at them from a survival perspective? What happened is that you know how many people are dying, but you don't know if these people were in the hospital. And if they were in the hospital, you don't know for how long they were in the hospital. And in that case, you don't know for how long they were infected. So it means that in this data, the duration is not directly observed. So it means that when you try to apply standard survival techniques, you have here a big challenge, because you need to develop some new methodology to be able to recover this duration, which is not explicitly on the data. So I will very briefly present the main feature of the statistical approach behind our benchmark proposal. Basically, the statistical approach is considering the main transitions in the pandemic, which are represented in this diagram at the beginning. And we start modeling this transition using counting processes. Why counting process? Because really we are just observing counts every day. So counting process seems to be the most natural and intuitive thing to consider here. When modeling these counting processes, we are assuming that the intensity of this transition, the risk in this counting process is dynamic, because we are aware that the things are changing along the pandemic. So the risk is different in the first month than in the second month, and so on. And then when we specify the counting process in these transitions, then we distinguish basically two types of counting process. And we do it depending on the quality of the exposure. The exposure here means the individual at risk. So the most difficult transitions are those starting in the infection. First, because the infection is not really what you are observing. You are not observing the infected people. You are observing the positive tested people. So it means that you are observing a subsample of the population you want, which probably is even biased. So modeling this kind of transition is quite difficult. And then we do it using some generalization of the so-called Fox process, accounting for overdispersion, which is important in this context. When you model the other transition starting in the hospital, then the situation is easier, because in that case, the exposure is well defined. You control the people at the hospital, and then you can use typical survival models for counting process. And then this model is modeling the data that you observe, but also the duration that you are not explicitly observing. So it means that you need to estimate the intensity recovered in this duration. And for that, we have proposed, we propose a novel iterative procedure involving non-parametric estimation. It means that for the risk, we don't assume some specific form, this functional form. So we provide the necessary flexibility to be able to adapt to the data. And when forecasting, then we extrapolate each of these transitions in the histogram, we do it incorporating external noise. And finally, we quantify, we account for the uncertainty using some bootstrap methods. So basically, this is the methodology in a nutshell without entering in details. And the thing I want to do now is to show you the kind of results that we are able to provide. So when we work on this, we consider data from different countries. And here I will show some analysis with data from France. They're taken from the public website, from the government, and they're taken in the period from 18th of March 2020 to 3rd of January 2022. It was almost at the end of the pandemic. And the kind of results we provide, first you will see the dynamic risk that we are estimating, and then from this you will see some typical survival indicators, and finally the forecast about the spread and the severity of the pandemic. So this is the dynamic risk that we are observing. So here I'm quantifying the risk of from the transition hospital to outcome, which could be recovery or death. And then, as I told you, the risk is dynamic. So it means that the date that you can see on the screen moving is the date where we are estimating the risk. It's changing quite dramatically along the period we are observing here. And from this risk, we are able to provide some indicators, for example, how much time people spent in the hospital, depending on where they were admitted. And then you can see the different admission dates in the horizontal axis. So you can see that it changed a lot. You can also see it by age groups, which was quite interesting. Another kind of indicator is about the chances that one has to live alive the hospital or to die in the hospital. So it's also changing dynamically in the time. And then for forecasting, I will show you here some kind of forecasting exercise, so you can see how the methodology can work. So I have chosen this period, which is from the beginning of the observation period to October 2020. Here you can see the infections. So we aim to forecast infection in a whole month. Actually, we are observing data, imagine we're observing data until the end of September, and then we want to predict what is happening. So the observed data is the black points you have here, and the future are these empty circles you have there. So you can see that we have chosen this month because actually infections increased a lot there. We were basically all locked down at that time of the year. And this is how our forecast works. So we provide first the fitted values for this data. So you can see it fits quite well. And then we provide two forecasts. The black forecast is, yeah?
Sorry.
Yeah? Sorry, you said something, Lola.
Sorry, 3 minutes.
Okay, 3 minutes, that's more than enough. So the black curve is just extrapolating the data we have, and the red curve is using the data, but incorporating a single piece of expert knowledge. So here the expert knowledge is actually epidemiological information summarized in the R number. So we are using the average R number for the period of forecasting, and then you can see that you really can recover quite well what you have there. Something similar we do for hospitalization, and it's the same. So data are not enough for forecasting. You need to use all the kind of information which epidemiologists are very good at providing this indicator, this number here. And our forecasting depth is something, again, similar. So that's basically the benchmark approach I wanted to present. So we have been describing this approach in several papers. Some of them are archived, one is published. And we have also provided an R package available at the CAN site that you can also use. So this is the team I work with. And I hope that you find interest in the work we have done. And thank you very much for the opportunity of presenting it here. Thank you.
Thank you very much, Lola. Very nice also. It is a different framework, but very interesting, and also useful tools that may be quite complex, as you mentioned at the beginning, to implement in that kind of data. The meeting, I think that is almost closed. So 1 minute we have for some question of the people in the audience or chat, because otherwise we have to finish, because we already are almost 45 minutes. So thank you very much before a short time. Please, some question or comments? Okay, it seems that it's time of saying bye. Thank you very much again for these beautiful talks, and also for this very different framework, but very, very, very focused on this kind of application for good. And also you are very, very representative in your career and research, a very good example of women in statistics and data science. So many thanks for being here. Thank you.